Welcome. We are live from the Eastview Food Court, and our food for thought today will be Hess's Law and also using standard heats of formation tables. Both methods can get you to solve the same type of problem. So here is a type of problem we're going to look at. This is in your homework packet toward the back of it. Use the toolbox to find the heat of reaction, or delta H, for the combustion of 1 mole of methane. So first we have to know what methane is, which is CH4. We're burning it, so we're combining it with oxygen. The two main products you're going to get are CO2 and H2O. We're going to assume we get CO2 gas and H2O gas in this reaction here. All right, so now we have a balanced equation for this. I'm guessing there's going to be giving off energy, even though we have to spark it to get it going. It's a burning of a hydrocarbon, and it's going to overall be an exothermic process. Well, this could be something you can measure directly, but what we're going to do is use heats of formation or a table of known equations to figure out this overall equation. Okay, so how does that work? I look at the compounds like CH4. And essentially, I'm going to look for the heat of formation of CH4. Sometimes you're given a short list or a table of those. I'm going to go to a toolbox, which I think is in your homework packet. I'm going to look at tool number 3, and the heat of formation of CH4 from its component elements. It releases 17.9 kcals. We're going to do things in kilojoules, so that's going to be 74.9 kilojoules being released. Now notice, this is on the product side, this is on the reactant side. I'm going to flip it. So instead of releasing 74.9 kcals, when I flip it, it's going to be absorbing 74.9 kcals. So let's go back and see what we do when we write that in there. So I just write CH4 plus 74.9 kcals gives me the carbon, the two hydrogens, and now this becomes a positive in the reverse direction. It is an endothermic process. Let's look at the next thing. I'm going to skip the elements. I'm going to think this might cancel out by itself. I'm going to go to the CO2, and I see CO2 in the second tool. I'm going to scroll down and look at the toolbox, and there's CO2. CO2 is on the product side. Carbon plus oxygen forming CO2 gives off 94 kcals, but again, we're doing in kilojoules, so you get 393 kilojoules right there. So notice CO2 is on the product side. I'm going to copy it down exactly like I see it here, including the energy term. So when I write it down exactly like I see it here, I'm going to do that, and it's negative 393. We're going to do it in kilojoules. And I'm sorry, this should be plus 393 kilojoules, but my delta H would be negative because energy is being given off. So this should actually be plus a positive 393 here, but this would be negative 393 right here. Okay, let's look at the last one, the H2O gas. So notice I'm going to go to the toolbox, and it's important to distinguish H2O liquid or H2O gas. It says gas, so I'm going to use this one right here. H2O is a product, so I'm going to use this right here. I'm going to take that and put it in right here, and I wrote it down, except what I did was I doubled everything, and I doubled everything because I got 2 in this equation. So if I have twice as much stuff, it's going to give off twice as much energy. So I take the H2 plus 1/2 O2 forms H2O and 241 kilojoules, and I double everything, and I say 2H2 plus O2 forms 2H2O, and you get the 483.6 kilojoules right there, or negative 483.6 because it's exothermic right there. I'm going to double check to make sure my equations add up to equal this and only these things. And a couple of things are going to cross out. The carbon here and the carbon here, the 2 H2s here and the 2 H2s here. Everything else matches a CH4. Notice O2 plus another O2 gives me 2 O2, which matches up here. So that oxygen did take care of itself. The CO2 is down here, and the 2 H2Os are right here. So I have the right combination of things to make this work. There could be other combinations of things that make this work, but it's ultimately going to funnel to the same correct answer. So I could look at this and say, oh, I win $74.90. I go release $393 and whatever cents. I go release $483.60. Overall, I lost more money or released more money than I absorbed. So I have a net loss. I add these two things together, subtract this. That's going to be the amount of my net loss. And I could write either one mole, I could either write plus 802 kilojoules over here, or I can add these up and say delta H equals negative 802 kilojoules. So when I say delta H, it's not telling me positive or negative. If I say negative, energy is automatically released. If I say positive, then energy is being absorbed. So ultimately, what does this mean? If 1 mole of gas, this reacts with 2 moles of this, forms 1 mole of this, 2 moles of this, gives off 802 kilojoules. Okay, there's another way to do this using standard heats of formations tables, which look like this. So look at this equation. And when we do standard heats of formation, we're just taking the standard heat of formation of the products minus the reactants. So I can look at this and say, oh, what's the standard heat of formation of CO2? I got to look at that table. And you have a table from your appendix here. And I also cut this out and put this in your Schoology thing. Now there is delta H values, delta G, which is Gibbs free energy, and S values for entropy, which we're going to deal with later, but not for a while. So you're looking at the delta H values, and I think the first one was CO2. So I need to find carbon dioxide, and I think I circled that one here, and that's negative 393.5. So that's the heat of formation of carbon dioxide from its component elements. So I'm going to take that negative 393.5. Let's go back up here, because that was one of my things that I had, negative 393.5. Now I know in my equation, I have what, 2H2O. So I'm going to have to take 2 times the heat of formation of water. All right, so again, I go to that table. I look over here, it's water as a gas, not as a liquid. So you want to make sure to take the right thing. I get the negative 242. However, I have 2 of them, so I'm going to have to double it, or I do and notice it was negative, so I got to do 2 times negative 242, which gives me negative 484. The last one, the reactants, I subtract. So I'm going to subtract the one for the CH4, and let's go and find CH4. And CH4 is right here, and that is negative 75. So subtracting a negative 75 gives me a plus 75. So that's why it ends up negative 393, negative 485, minus a minus gives me a plus 75. And I take these two things, add them up, they're negative 800 some. I add the 75 and I get negative 802.5. Notice I did not include this here because elements in their free state, they're already formed. So the heat of formation would be 0 right here. An element in its free state would be that. So heat of formation is for compounds, okay, from elements in their free state. If something's already in its free state, there's no need to apply any energy to get there. Should the two answers be the same? Yes. Are they the same? 800 minus 802.0 minus negative 802.5. I think you have things from maybe a 20-year-old textbook and a table and about a 50-year-old toolbox. So that's still pretty good agreement for some different things that we're working with. All right, so that is Hess's law and standard heats of formation, 2 ways to do the same thing. In AP, you'll be asked to do both methods at various times. Thank you.